All right, guys, so for number 59, the problem says a tree loses water to the air by the process of transpiration at the rate of 110 GH. This water is replaced, or G per H. This water is replaced by the upward flow of sap through vessels in the trunk. If the trunk contains 2,000 vessels, each 100 μm in diameter, what is the upward speed of the sap in each vessel? The density of the tree sap is 1040 kg per meter cubed. All right, so to start this problem, strategy-wise, I'm going to start the way we start every problem, which is writing what we want, which the problem says is the velocity of the sap going up the tube, which I'm going to use the symbol VSAP for. So then we're going to write what we know. So what we know in this case, I drew a picture here, so we know the tree looks something like that, where there's a cross-sectional area and the velocity of the sap is pointing upward direction-wise. We also know that the rate of the mass escaping with respect to time is equal to n, or the number of tubes, times density of fluid, times cross-sectional area times v, which are both found in this photo here, or this figure. So again, now that we have up here, we have what we are looking for in an equation. Should have written VSAP, but let's add that in right now. So we have what we're looking for in the equation right here, so now we just have to isolate it. So we solve for V here, and we get VSAP is equal to dm dt over n rho a. And then just to break this down further, because a is still an unknown variable, we know a is equal to pi d squared over 4, so we can substitute that in, and then we get VSAP is equal to dm dt over n rho pi d squared over 4. So this is an answer, and we know it's an answer because we have what we were looking for, VSAP, written in terms of only known variables. So dm dt is known and given in the problem, and is known and given in the problem, and the rest of these are as well. So if you plug in numbers, so this is the answer in symbolic form. If you plug in the numbers given in the problem, you should get 0.187 meters per second. So common pitfalls with this problem. Using rates can get a bit confusing because it's given, if you're reading through the problem a bit too fast, you can see that it's just given as a number, 110, but it's important to remember that they're saying rate here. So it is in fact going to be written as the rate of mass escaping. Oh, sorry, can't see that. The rate of mass escaping with respect to time. So it's important to remember that number represents a rate of change. And yeah, this problem is fairly simple, I would say, compared to 42. And contextually, I would say this problem is just trying to get you to understand how to apply formulas from transpiration. And it's a pretty simple case of problem solving where what we want is only a couple steps away from what we want is fairly close to being able to isolate already. As you can see, it only took one step to get this, and then we could already start isolating. Unlike some other problems where you will have to start from much more basic terms and start breaking things down over and over and over to get to the point where you have this. But here, we get it fairly quickly. And yeah, that's about it. Thanks for watching, guys.